So we've argued, at least a plausibility argument, that the curve f of xy equals c is at every point perpendicular to the gradient of f evaluated at the point xy. Geometrically, if this is our curve f of xy equals c, then at every point on that curve, again assuming a suitably behaved function f of xy, we have a tangent vector, and we could regard this as a unit tangent vector, but it doesn't have to be a unit tangent vector. So we have a vector here. This would be the vector, well, the tangent vector at this point. I'm not going to put a label on it. What we're saying is that the gradient at this point will be along the line perpendicular. The gradient could be in this direction, could be in this direction. Since it's going to interfere with my labeling, if I put it in this direction, I'm going to assume, okay, the gradient is in this direction, perpendicular to the tangent vector. So right there's my gradient of f evaluated at this point. My gradient of f evaluated at this point be in this direction, and not to confuse the gradient with curvature or any other property of this curve. The gradient isn't necessarily of constant value and generally won't be. This vector is a little shorter than this one. I'll intentionally make this one a little longer. At every point, the gradient is perpendicular to the tangent vector, which means that at every point, if we move in the direction of the tangent vector, the value of our function f of xy stays constant. And if we move in the direction perpendicular, we're going to have a direction in which the magnitude of the function changes at a maximum rate. So the function will change fastest in this direction, this direction, this direction. The magnitude of the function will change fastest. And the magnitude will also change fastest in the direction of the negative magnitude, negative gradient. But the direction of the gradient will be the function of maximum rate of increase. If, for example, we have a set of level curves for a function, let's let this be our c equals 1 curve, our c equals 2 curve, our c equals 3 curve, and so forth. Then, if I'm at this point, I know that my gradient is in the direction of maximum increase in the value of f, so that the gradient will be in the direction from the c equals 1 to the c equals 2 curve, perpendicular to a tangent vector. So here would be my gradient of f evaluated at this point. And at other points of the curve, the gradient is always perpendicular to the curve. So let me just draw a few more vectors indicating gradients. Okay, perpendicular to this curve, I guess, is going to be in this direction. Perpendicular here will be in this direction. And remember that it doesn't matter whether the curve is, whether the gradient is in the direction of the inward normal or the outward normal. It could be either, and that could change from one point of the curve to the other. So my gradients might look very much like this. The gradients along the c equals 2 curve might look like this. That one's going to kind of overlap the other curve. And I'm not attempting to draw these gradients to scale. We'll consider the scale in a second. I'll make a couple of comments. So, assuming the c equals 4 curve lies out here, we would have similar directions for the gradients on the c equals 3 curve. Always perpendicular to the curve, always in the direction in which the function is increasing. I'll also comment that if the behavior of this function is relatively smooth over this region, and no serious anomalies in the higher derivatives or the derivatives of the gradients and so forth, the closer these curves are together, the faster the function is changing, so the greater will be the gradient. So, for example, between these 2 points, we change from c equals 2 to c equals 3 much more quickly than, for example, we change from c equals 1 here to c equals 2 here. So this gradient vector would actually be relatively somewhat longer than the gradient vector here. And the closer the contour lines are, the closer our level curves at equal changes in the constant value, the greater will be the gradient. So when the curves are very close together, the gradient will be great. When the curves are farther apart, the gradient will be less. I haven't represented that on this graph, but that's something you should think about.